Welcome to the Sleepy Scholar. It's lovely to have you here tonight. Wherever you are right now, whatever corner of the world you've settled into, I'm glad you found your way here. Maybe you're lying in bed with the blankets pulled up, just so, the kind of warm where your feet have finally stopped being cold. Maybe you're on the couch with a lamp still glowing softly in the corner, the rest of the room gone dark. Maybe you're on a train or long drive home, or simply sitting somewhere quiet with a cup of something warm cooling beside you. It doesn't matter where you are. You're here, and that's enough. So before we begin, I'd love to know, where in the world are you watching from tonight? What time is it in your corner of the night? If you'd like, leave it in the comments. There's something gently lovely about the thought of all of us, scattered across so many time zones, all settling in to drift through the same strange and beautiful idea together. Some of you are watching as the sun goes down, some of you in the deep middle of the night. Some of you perhaps are awake far too early, the world outside still grey and asleep. Wherever you are on that great spinning clock, I'm glad you're here. And if you enjoy these slow journeys and you'd like more nights like this one, a quiet like and subscribe really does help this sleepy little channel keep going. Small creators like me genuinely rely on it. It's the small, soft thing that lets these wanderings continue. And to those of you who have already subscribed, who come back night after night, thank you. Truly. It means more than I can easily say. Now let me make you a promise, and let me make it the kind of promise you can lean back into. We are going to move slowly tonight. Slowly and gently, one mystery at a time. There is no rush here, no race to the finish, nothing you need to keep up with. I'll try not to make this so interesting it keeps you awake. But if it does, well, at least you'll have learned something. A fair trade, I think. And here is the part I want you to really hear. You do not have to understand everything. You do not have to hold on to every word, or grasp every idea, or remember a single name. If your eyes grow heavy, let them close. If your attention drifts off somewhere soft and you lose the thread, that's perfectly fine. The ideas will still be here. They're not going anywhere. The universe has been keeping these secrets for billions of years, patient as anything, and it will happily wait for you. So let go of the need to follow along. Just let the words wash over you like the sound of rain on a window. And if you fall asleep before the end, then you've done exactly what you came here to do. So, settle in. Get comfortable. Let your shoulders drop down from wherever they've been hiding up near your ears all day. Take a slow breath in and a slower one out. Tonight we're going to think about something that sounds, at first, like a contradiction. A puzzle that seems to fold in on itself. Something that, when you first hear it, makes you tilt your head and frown just a little in the dark. Here is the question we'll be drifting through tonight. Astronomers went looking out into the universe and they found galaxies, great islands of stars, drifting in the deep, that appear to contain almost no dark matter, almost none at all. And the strange thing, the thing that makes this such a lovely little riddle to fall asleep to is this. Finding a galaxy with no dark matter sounds like the theory breaking. It sounds like proof that the whole idea was wrong all along. And yet somehow it turned out to be one of the strongest pieces of evidence we have that dark matter is real. A galaxy missing its dark matter used as proof that dark matter exists. It sounds backwards, doesn't it? It sounds like nonsense. And by the end of our slow walk through this, I hope it will sound like the most natural thing in the world. Let me give you the heart of it now, gently. And then we'll spend the rest of our time slowly turning it over in our hands, looking at it from every soft angle until it makes perfect sense. The whole riddle comes down to a single quiet distinction. The difference between a substance and a rule. Think about it this way. A substance is a thing. It's stuff. It's something you can have a lot of or a little of or none at all. Water is a substance. You can fill a glass to the brim or pour out half or empty it entirely and have a glass with no water in it. Sand is a substance. You can have a whole beach of it or a single handful or none. The amount can change. You can add it, you can take it away, you can lose it entirely. That's what it means to be a thing. A rule is something else completely. A rule is not a thing you can hold. It's not stuff. It's a law about how the world behaves, and the very nature of a rule, a true rule, a law of nature, is that it applies everywhere, to everything, all the time, with no exceptions. Gravity, as we usually think of it, is a rule. It doesn't switch off in one room and switch on in the next. It doesn't apply to some apples and not others. A rule, a real law of the universe, cannot make exceptions. If it did, it wouldn't really be a law at all. Now hold those two ideas in your sleepy mind side by side, a substance, which you can lose, and a rule, which you cannot escape. Because here's the thing, for decades, there have been two great competing explanations for the strange behavior we see in galaxies. We'll meet both of them properly tonight, slowly and fairly, and I want you to know up front that both of them are serious ideas taken seriously by serious people. One explanation says there is a hidden substance out there, something we cannot see, an invisible kind of matter woven all through the galaxies, adding its weight, pulling with its gravity. We call that dark matter. The other explanation says there is no hidden substance at all. Instead, it says our rule for gravity is simply a little bit wrong. And if we corrected the rule, we'd explain everything we see without needing any invisible stuff. That idea is called modified gravity. And for the longest time, these two ideas were very hard to tell apart. They both explained the things we could see. They both fit the data. It was like two suspects who both have an alibi for the same crime. How do you ever tell which one is telling the truth? And that is exactly why these strange, nearly empty galaxies matter so much. Because if dark matter is a substance, a thing like water in a glass, then of course you could find a galaxy that's missing it. You could find a galaxy where, for one reason or another, the invisible stuff got poured out. An empty glass is no surprise at all if you believe in glasses of water. But if the strange behavior of galaxies comes from a modified rule of gravity, a universal law that applies everywhere with no exceptions, then you should never, ever be able to find a galaxy where that rule doesn't apply. You cannot have a galaxy where the law of gravity simply forgot to show up. A rule that makes an exception is not a rule. So a galaxy that behaves by the plain, ordinary, old-fashioned rules of gravity, a galaxy that needs no extra anything, is precisely what you'd expect if its invisible substance had simply gone missing. And it's precisely what a modified universal law of gravity should forbid. These quiet, transparent galaxies aren't a hole in the theory. They're the test the universe set up for us all on its own. The control experiment run for free out there in the dark, waiting for us to notice. That's the whole riddle. You can't lose a law, but you can lose a substance. And so a galaxy that lost something is telling us, very quietly, that the something was real all along. There, that's the idea we'll be drifting through. Now let's slow right down and start where the story actually starts. Let's go back, way back, to the very first hint that something invisible was out there at all. And to understand that, we don't even need to leave home. We can start in our own solar system with the planets you already know. Picture the sun sitting there in the middle, holding everything in its grip. And picture the planets going around it, each one tracing its slow, patient circle. Now here is something true and lovely about how those circles work, and it's a rule you can feel in your bones once you see it. The closer a planet is to the sun, the faster it has to move. The farther out it is, the slower it goes. This isn't a coincidence. It's the very heart of how gravity and orbits work together. Think of it like this. Imagine you're swinging a small weight on a string around your head. If the string is short, you have to whip it around quickly to keep it up. If you let out a lot of string so the weight is way out, at the end of a long line, it swings around much more lazily, much more slowly. The sun's gravity is like that string, except it gets weaker the farther out you go. So a planet far away feels only a gentle pull, and it only needs to drift along slowly to stay in its orbit. A planet up close feels a fierce pull, and it has to race along to keep from falling in. And the numbers bear this out beautifully. Earth, where you are right now, is moving around the sun at about 30 kilometers every single second. 30 kilometers a second. That's faster than you can really imagine, faster than any rocket, and you don't feel a thing. You're on a planet hurtling through space at that speed, and yet here you are, lying still and warm in your bed. Now go all the way out to Neptune, the far blue planet on the cold edge of our solar system. Neptune is moving at only about 5.5 kilometers a second, far slower. Earth at 30, Neptune at 5.5. The outer planet dawdles along, while the inner ones rush. This pattern, faster when you're close, slower when you're far, has a name. It's called a Keplerian decline, named after the astronomer who first worked out the laws of how planets move. But you don't need to remember the name, just hold on to the feeling of it, the shape of it. Out at the edges, things slow down. That is what gravity, the gravity we know, predicts. That is the rule working exactly as it should in our own backyard. Now hold that picture in your mind, the slowing edges and Mordehai, and let's drift out much, much farther, out past our sun, past the nearest stars, out to the scale of an entire galaxy, a great spiral of hundreds of billions of stars all turning together in a vast, slow wheel, like a cosmic pinwheel turning once every few 100 million years. A galaxy is, in a way, just a bigger version of the solar system. There's a great concentration of stuff toward the middle, all those stars packed densely in the bright central bulge. And then the stars thin out as you go toward the edge, where they trail off into the faint, dim outskirts. So you'd expect the very same rule to hold, wouldn't you? You'd expect the stars near the crowded center to whip around quickly, and the stars way out at the lonely edge, far from most of the galaxy's mass, to drift along slowly. Just like Neptune, out on the cold rim, taking it easy. The rotation should decline as you move outward. The edges should slow down. That's what the mass we can see should produce. That's what astronomers expected to find. That's what the rule of gravity, our trusted rule, the one that works so perfectly for the planets, told them they should see, and it isn't what they found, not at all. This is where the story turns, and I want you to stay with me here, even as you grow drowsy, because this is the original mystery, the very crack in the wall through which everything else came pouring. When astronomers actually measured how fast the stars at the edges of galaxies were moving, they found that the stars out on the rim were not slowing down. They were orbiting at very nearly the same speed as the stars much closer in. The edge of the galaxy was keeping pace with the middle. Let that sink in slowly. In our solar system, Neptune crawls along at 1/6 of Earth's speed, but in a galaxy, the equivalent of Neptune, a star way out on the faint edge, is racing around almost as fast as a star near the bright, crowded heart. The slowdown that should happen, the gentle decline toward the edges, simply doesn't happen. Instead of the rotation curve dropping off as you go outward, it stays flat. Flat and level, like a calm sea stretching out to the horizon. Astronomers call this a flat rotation curve, and it was, and still is, one of the great puzzles of the cosmos. Stars at a galaxy's edge orbit far too fast for the visible matter to hold them. That should be impossible. With only the matter we can see, those outer stars are moving so quickly that the galaxy's gravity shouldn't be able to keep them. They ought to be flung off into the dark, like a child losing their grip on a fast-spinning merry-go-round. And yet the galaxies don't fly apart. They hold together, turning calmly, edge keeping pace with center, as if there were a great deal more mass holding them in their orbits than anything we can actually see. As if the galaxy were far, far heavier than all its glowing stars combined. Something extra was holding them in. Something with weight, with gravity, that we could not see. Some invisible hand keeping the fast-moving outer stars from flinging off into the night. Now this kind of thing, a galaxy spinning too fast to hold itself together, had been whispered about even earlier by a few sharp-eyed thinkers. We'll meet a little later in our journey. On another night this story continues. But for a long time it was just a whisper, a curiosity. One of those odd little footnotes that scientists noticed and then set gently aside, half believing they must have made a mistake somewhere. It takes a great deal to make a whole field of careful, cautious people change their minds. It takes more than a whisper. It takes someone patient enough and careful enough to measure the thing again and again in galaxy after galaxy until the whisper becomes a sound too loud to ignore. And so slowly we come to the person who did exactly that. The astronomer who took this strange anomaly and turned it from a curiosity into a problem the whole field could no longer look away from. Her name was Vera Rubin. In the 1970s, working alongside an instrument builder named Kent Ford, Vera Rubin set out to do something that sounds simple, but was, in practice, painstaking and slow and quietly heroic. She set out to measure, carefully and precisely, how fast the stars and gas were moving at different distances out from the centers of spiral galaxies. Not just one galaxy, not two, dozens of them. Galaxy after galaxy after galaxy, including our great neighbor Andromeda. The galaxy astronomers also call M31, the nearest big spiral to our own, a faint smudge of light you can see with your own eyes on a dark night, which is in truth a whole other island of 1 trillion stars. To do this, Rubin and Ford used something called a spectrograph. Now, a spectrograph sounds like a complicated thing, and in its engineering it is, but the idea behind it is rather beautiful and simple, so let me decode it for you gently. When light comes from something that's moving toward you or away from you, the light gets very subtly stretched or squeezed. It's the same thing that happens with sound, with a train whistle or a passing car. The pitch rises as it comes towards you and drops as it goes away. Light does this too. Light from something moving away from you gets stretched toward the red end of the rainbow. Light from something coming toward you gets squeezed toward the blue. A spectrograph is simply a very, very sensitive instrument that spreads starlight out into its rainbow of colors and measures that tiny stretch or squeeze. From that, you can work out how fast a star or a cloud of gas is moving and in which direction. It's a way of reading the speed of things impossibly far away just from the color of their light. A speedometer for the stars built out of rainbows. Kent Ford was a gifted builder of exactly these instruments, and the spectrograph he made was unusually sensitive. Sensitive enough to catch the faint light from the dim outer edges of galaxies, where the stars grow sparse and the glow grows thin. That sensitivity mattered enormously because the whole question lived out there at the edges. Anyone could measure the bright, crowded middle. The mystery was in the faint rim, and you needed exquisitely sensitive eyes to read the speeds out there. And so, night after patient night, Vera Rubin pointed their instrument at galaxy after galaxy and read the speeds of the stars from the colors of their light. And in galaxy after galaxy, she found the same thing, the same flat curve, the same impossible result. The stars at the edges, where they should have been slowing down to a Neptune-like crawl, were instead keeping pace, orbiting just as fast as the stars far inside. Not in one galaxy, not as a fluke, in dozens of them. Again and again and again. It was everywhere she looked. It was a general law of how galaxies behave, not a quirk of one peculiar object. And that is what changed everything, because a single strange galaxy you can shrug off. You can say, well, perhaps that one's odd, perhaps we measured wrong, perhaps there's some special explanation. But dozens of galaxies, all telling the same impossible story, measured carefully by a careful scientist with a beautiful instrument that you cannot wave away, that you have to explain. Vera Rubin took something that had been a faint, dismissible whisper at the edge of astronomy, and she made it solid, undeniable, a problem sitting squarely in the middle of the room that every astronomer now had to find a way to account for. She converted a piece of speculation into a fact that demanded an answer, and there are really only two kinds of answer you can give to that fact. Only two ways out of the room. Either there is a great deal of invisible mass out there, hidden in and around every galaxy, adding the extra gravity that holds those fast-moving edges in place like a substance we cannot see, or our very rule for how gravity works is subtly wrong and needs to be corrected. A rule we got slightly mistaken, a missing substance, or a flawed rule. Those are the two doors, and everything we'll explore from here, every name and every discovery and every clever argument, is really just the long, patient story of trying to figure out which of those two doors leads to the truth. It's worth pausing here, just for a soft moment, on Vera Rubin herself, because there's a quiet human thread in this story too. She did this enormous foundational work that reshaped our entire picture of what the universe is mostly made of. And for all of it, she was passed over again and again for the highest honors that science gives. Many people have said in the years since that hers was among the most important observational discoveries of the whole 20th century, and that she ought to have been recognized for it in a way she never quite was in her lifetime. She died in 2016. I don't say this to stir anything up in you as you're trying to rest, only to let her name sit here for a moment in the quiet, the way it deserves to. Vera Rubin, the woman who read the speed of distant stars from the color of their light, and in doing so, found the first clear fingerprint of something invisible holding the universe together. So here is where we've arrived on this first gentle stretch of our journey. We have a fact, solid and strange and beautifully established. Galaxies spin too fast at their edges to hold themselves together with the matter we can see. The rotation curves are flat when they should decline. Something is missing from our picture, either a great deal of unseen stuff or a great deal of unseen truth about gravity itself. And we have our riddle for the night waiting patiently in the dark ahead of us, because if the missing thing is a substance, then somewhere out there a galaxy could be found that simply doesn't have it, an empty glass. And if the missing thing is a rule, then no such galaxy could ever exist, a law with no exceptions. And the universe, as it turns out, was kind enough to give us exactly the test we needed to tell the two apart. But we're getting ahead of ourselves, and there's no rush, none at all. Before we go and meet those strange, transparent galaxies, before we weigh the rival idea and follow the clever arguments out into the deep, there's more of the early story to tell. There's an astonished astronomer staring at a cluster of galaxies long before Vera Rubin ever picked up her spectrograph, finding them moving so fast they should have flown apart decades earlier. There's the great cosmic accounting of just how much of this invisible stuff there must be, and the answer is far stranger than you'd guess. And there's the rival explanation, the one that says maybe there's no invisible stuff at all, maybe we just have gravity slightly wrong. We'll give that idea its full and fair hearing because it's a good one and it has real triumphs to its name. But all of that is for the next part of our slow wander through the dark. For now, just rest with the picture we've built. A great wheel of stars turning calmly in the night. Its edges racing along far faster than they have any right to. And some great, patient, invisible hand holding it all gently together. A hand we cannot see, cannot touch, cannot catch, and yet whose grip is written across the sky in the speed of every distant star. Stay with that image as you drift, the turning wheel, the unseen hand, the quiet, enormous mystery of the thing that makes up most of everything and never once shows its face. We'll pick up the thread from here. Welcome to the Sleepy Scholar. It's lovely to have you here tonight, whoever you are, wherever you've curled up to listen. Maybe you're under a heavy blanket, with the lamp still glowing soft and orange in the corner. Maybe you're on a train, watching the dark slide by. Maybe it's very late and you really should have been asleep an hour ago. Whatever brought you here, settle in. You're welcome, and you're in no hurry at all. And before we wander any deeper, tell me, where in the world are you watching from tonight? What time is it in your corner of the night? I always love to imagine all of you, scattered across the planet, listening in the same quiet dark. If you enjoy these slow journeys and you'd like more of them, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think.
And to those of you already here, already part of this, thank you. Truly, now settle back in. I'll try not to make tonight's mystery so interesting that it keeps you awake, but if it does, well, at least you'll have learned something lovely about the universe before dawn. A fair trade, I think, so if you drift off somewhere in the middle, that's perfectly fine. The ideas will still be here when you wake. The galaxies aren't going anywhere.
We'll move slowly, softly, one small wonder at a time, and you never have to grasp every detail to feel the shape of the thing. Just let it wash over you. So here is the question we're holding tonight, the one quiet riddle at the heart of it all. It sounds like a contradiction, the kind of thing that shouldn't make sense. We are going to talk about finding galaxies with no dark matter, and how that absence, that emptiness, might be the very best proof that dark matter is real.
I know, it sounds backwards, like saying an empty cup proves the water exists, but sit with it a moment because there's a beautiful little distinction buried in there, and once you see it, you can't unsee it. Think of the difference between losing a law and losing a substance. You cannot lose a law. A law of nature applies everywhere to everything with no exceptions. It doesn't switch off for one galaxy and stay on for the next. But a substance is a thing.
And a thing you can have a great deal of, or a little of, or none at all. You can lose a substance. It can be taken away, stripped off, left behind. That's the whole test, really. That's what these strange, transparent galaxies give us. A way to tell the difference. If what holds galaxies together is some modified rule of gravity, a law, then it must hold for all of them, and you should never find one behaving as though the rule doesn't apply. But if it's a substance, invisible, but a substance all the same, then somewhere out there something might have lost it. And those two possibilities make different predictions. The universe kindly ran the experiment for us. We'll get to those galaxies, two of them in fact, called DF2 and DF4, but not yet. No rush. Let's go back instead to where the trouble actually started. Back to the thing that made anyone suspect there was invisible mass at all. And it begins with something that should be utterly ordinary. The way things move in circles. Picture our own solar system for a moment. The planets swinging around the sun. And here's a thing you might not have noticed. They don't all move at the same speed. The closer a planet sits to the Sun, the faster it races. The Earth hurtles along at about 30 kilometers every second, but poor distant Neptune, way out in the cold, only manages around 5.5. The farther out you go, the slower things drift. The Sun's grip loosens with distance and the orbits relax into a gentle crawl. Astronomers call this Keplerian, orbital speed falling off with distance, like ripples losing their energy as they spread. It's tidy. It's exactly what you'd expect when nearly all the mass is bundled up in the center, in the Sun. Now hold that picture and turn your gaze to a whole galaxy, a great spiral wheel of stars, hundreds of billions of them. Most of the visible light, most of the obvious matter, crowds toward the bright bulge in the middle. So you'd think, wouldn't you, that the same thing should happen. Stars near the center should whip around fast, and stars way out at the faint, lonely edge should drift along slowly, just like Neptune. The light is in the middle, so the mass should be in the middle, so the grip should fade as you move outward, but it doesn't. That's the catch. That's the strange, quiet shock of the whole thing. When astronomers measured how fast stars actually move at the outer edges of spiral galaxies, the speed didn't fall off at all. The stars at the far rim were orbiting just as fast as the ones much closer in. The rotation curve, as they call it, that line tracing speed against distance, didn't slope down the way Kepler said it should. It went flat, stayed flat, stretched out level, far past the edge of the visible disk, as if some unseen mass were out there too, hidden in the dark, pulling those distant stars along faster than they had any right to go. With only the matter we can see, the speed should decline beyond the bright disk. It simply does not. The stars at the edge orbit as if there's far more mass holding them than any telescope can find. And that gentle, stubborn flatness is the foundation of the whole mystery, the first crack of light through the door. Now, it's one thing to notice this in a single galaxy. You might wave it away, a quirk, a one-off, a strange galaxy with strange habits. And for a while, that's roughly where things sat, a curiosity, a puzzle for someone else to solve someday. Enter Vera Rubin and Kent Ford. In the 1970s, these two set out to actually nail the thing down, not with one galaxy, but with dozens. Rubin and Ford had a wonderfully sensitive spectrograph, an instrument that could read the faint shift in starlight and translate it into speed, telling them exactly how fast different parts of a galaxy were turning. And, patiently, galaxy after galaxy, they measured. Spiral after spiral, including our great glittering neighbor Andromeda, M31, that vast wheel you can almost see with the naked eye on a clear, dark night. And every time the same answer came back, flat, flat, flat. The stars at the edges refusing to slow down. It wasn't a quirk of one peculiar galaxy. It was everywhere. It was a rule of the spirals, written into all of them, patient and undeniable. Rubin and Ford's careful work took the flat rotation curve and turned it from a half-noticed oddity into something the whole field had to reckon with. They turned a vague speculation into a hard, real problem, a problem with a name beginning to gather around it in the dark. Because now the question was unavoidable. If the visible stars can't account for these speeds, then what can? What invisible thing is out there, threaded through every spiral, holding the racing edges in place with a grip we cannot see? We'll follow that question into deeper water soon, but not tonight. Rest for now, with Vera Rubin at her instrument in the quiet of the observatory, watching the same impossible answer arrive again and again, slowly realizing she was looking at the fingerprints of something that had never shown its face. And there's a satisfying symmetry to that image. Vera Rubin, quiet, patient, watching the impossible repeat itself. But before we follow the flat rotation curve toward its answer, we need to travel back further than the 1970s, back to a man who had the same idea in a rougher form 40 years earlier, and who was, for 40 years, largely ignored. His name was Fritz Zwicky. And in 1933, he did something that should have changed everything. Zwicky was Swiss-American, an astronomer at Caltech, and by all accounts a man who was not especially gentle about telling you when he thought you were wrong. He had a gift for noticing things other people walked past, and he had the confidence, some might say the stubbornness, to say so loudly. In 1933, he turned his attention to something much larger than a single galaxy. He was looking at the Coma Cluster. The Coma Cluster is one of the great collections of the observable universe, a swarm of galaxies, thousands of them, bound together by their mutual gravity somewhere around 300 million light-years away. It is one of the nearest large galaxy clusters to us, rich and dense, a city of galaxies rather than a neighborhood. Zwicky was measuring the motions of individual galaxies within it. Now here is the thing about a gravitationally bound cluster. If you know how much mass is holding it together, you can calculate how fast the members can move without escaping. Too fast, and they'd simply fly apart. The cluster would dissolve. The fact that it exists at all tells you the gravity is strong enough to contain the motion. Zwicky measured the speeds of galaxies in the Coma Cluster, and he found that they were moving, relative to each other, across the cluster, far, far faster than they should have been. He added up all the visible mass. Every galaxy he could see, every luminous thing in that swarm. And the math came out the same way it would come out for Vera Rubin 4 decades later. The visible matter was not nearly enough. There wasn't enough gravity from what he could see to keep those galaxies from flying apart. The cluster should not exist. And yet, rather obviously, there it was. Zwicky concluded with the directness that characterized everything he did that there must be vastly more mass in the cluster than the luminous matter accounted for. He coined a term for it. In German, he called it Dunkel Materie, dark matter, a name that is really just a description of what it refuses to do, shine. His estimate of how much missing mass was required was striking. The invisible component, he thought, must be several hundred times more massive than everything he could see. The specifics of that figure have been refined enormously since, but the essential shock of the claim has held. There is far more out there than meets the eye, far more than our instruments catch. And the response from the astronomical community? Largely nothing. Zwicky's results sat in the literature, acknowledged in a distant way, but not really taken up as a crisis. Perhaps it seemed too speculative. Perhaps the measurements seemed too uncertain. Perhaps dark matter sounded like a placeholder, a polite way of saying we haven't figured this out yet. Whatever the reason, his prophecy went largely unheeded for 40 years. 40 years in which Zwicky watched the field move in other directions, never quite crediting him with the thing he had found. It took Vera Rubin's meticulous galaxy-by-galaxy work in the 1970s to make the problem feel inescapable. But Zwicky had seen it first from the cluster scale in 1933. He had named it. He had pointed at the dark, and the dark had waited for him, patient and unblinking, until everyone else finally caught up. There is something almost poignant about that. The prophecy that sat in a drawer for 40 years, while the universe kept the secret it had already given up. Now, what exactly is dark matter? What do we actually mean by that name beyond the simple fact of its darkness? Here is what we know with confidence. Dark matter does not interact with light, not in any direction. It doesn't emit light, so you can't see it glowing. It doesn't absorb light, so you can't see it as a shadow against bright backgrounds. It doesn't scatter light, so it's perfectly invisibly transparent to every photon that passes through it. Electromagnetic radiation of every kind. Radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. All of it passes through dark matter as though the dark matter simply isn't there. The only way we know dark matter is there at all is through gravity. It pulls. It bends the paths of things moving near it. It shapes the way galaxies spin and the way clusters hold together. It leaves fingerprints everywhere in the universe's large-scale structure. But it never once raises its hand and says, "Here I am." Every instrument we have built to catch particles was built to catch something that interacts with light or with ordinary matter in some way.
And dark matter refuses to play by those rules. Think of it this way. Imagine you're in a dark room and you know there is furniture in it. You can feel the floor vibrating slightly, the way sound bounces off something solid, the way the air moves differently around large shapes. You know the furniture is there, but when you turn on the light, nothing appears. The furniture bends sound and changes the airflow, but it is made of something light doesn't touch.
You can map it roughly by its effects, but you cannot see it, you cannot put your hand on it. It is real, its effects are undeniable, but it operates on different terms. That is dark matter, detected only gravitationally, present everywhere, threaded through galaxies and clusters and the great web of space itself, and completely, stubbornly invisible. Which raises an obvious question: just how much of it is there? The answer, when you hear it, tends to make people go quiet for a moment. The Planck satellite, a European Space Agency mission that mapped the cosmic microwave background in exquisite detail, with its most precise results published in 2018, gave us our best accounting of what the universe is actually made of. And the picture it painted is humbling. Ordinary matter, the stuff made of protons and neutrons and electrons, the atoms that make up every planet, every star, every ocean, every person, every book, every breath of air you've ever taken, accounts for roughly 5% of the total energy content of the universe. 5 out of 100. Dark matter accounts for roughly 27%. And the remaining 68%, that belongs to something else entirely. Dark energy, the mysterious force or property of space that is driving the universe's expansion to accelerate. But that is a different story and not the one we're following tonight. One orientation sentence, and we'll let it rest. Dark energy is real and it dominates the universe's fate, but its nature is even more uncertain than dark matter's, and it does not show up in galaxy rotation curves or globular cluster motions. So we leave it in the background where it belongs for now, because the number we need to sit with is this one. Dark matter outweighs ordinary matter by roughly 5 to 1. For every kilogram of atoms, or every kilogram of the stuff everything you have ever touched is made of, there are approximately 5 kilograms of dark matter, 5 times as much. And yet it registers on none of our senses. It touches none of the particles we're built from. It is the dominant material of the universe, and it is, in a very real sense, a completely different universe running alongside ours, feeling the same gravity, but otherwise living by different rules. That 5 to 1 ratio is worth letting wash over you for a moment wherever you are. The ordinary matter, the stars, the clouds, the galaxies we've been talking about, that is the minor ingredient, the afterthought. The dark matter is the main event, and we have had no direct way to catch even a single piece of it. Now some people, and this is a reasonable response, heard all of this and thought, wait, before we invent an entire invisible substance that outweighs everything we can see 5 to 1, should we perhaps consider that we might just be wrong about gravity? Should we perhaps consider that the equations we're using to calculate these speeds might need to be corrected rather than the ledger of what's out there? That is not a foolish question. That is, in fact, a very good one. And in 1983, a physicist named Mordehai Milgrom gave it a serious answer. Milgrom was an Israeli physicist working at the Weizmann Institute of Science, and his idea was elegant in the way that the best alternative theories tend to be. It didn't require inventing new invisible stuff. It required revising a rule. Specifically, it suggested that Newton's law of gravity, which we've trusted for centuries and which works beautifully within the solar system, might not be the full story at very, very low accelerations. His theory is called MOND, Modified Newtonian Dynamics. And here is the core of it. In our everyday experience and in the solar system, gravitational accelerations are relatively large. Earth's gravity pulls you down at about 9.8 meters per second squared. Even at the edge of the solar system, where Neptune drifts along at about 5.4 kilometers per second, the Sun's gravitational pull is still a reasonably robust quantity. In these regimes, Newton's gravity works perfectly. Einstein's general relativity refines it slightly, but Newton is an excellent approximation. But deep in the outskirts of a galaxy, out where the stars are sparse and the gravitational pull from the galaxy's center is growing very faint, the acceleration experienced by a star can become extraordinarily small. Milgrom proposed that below a critical threshold, a characteristic acceleration scale he called A0, approximately 1, 2 times 10 to the power of negative 10 meters per second squared, the behavior of gravity, or perhaps the behavior of inertia itself, changes. It becomes more gentle in its fall-off. Instead of gravity weakening as sharply as Newton's law says it should at large distances, it weakens more slowly, and this more gradual weakening is just enough, just precisely enough, to keep those outer stars orbiting at the same speed as the inner ones, producing the flat rotation curve without any dark matter at all. Let's be clear about just how small that acceleration threshold is: 10 to the negative 10 meters per second squared. To give you a sense of that, if you took a single strand of human hair and placed a tiny ant at one end of it, and you accelerated that ant toward the other end so slowly that it would take the ant more than 3 years just to traverse the length of the hair. That's roughly the kind of acceleration Milgrom is talking about, vanishingly small. The kinds of accelerations that only become relevant at the edges of galaxies, far from their luminous centers, where the gravitational field has stretched thin. Below that threshold, MOND says, things work differently. Above it, Newton holds. The solar system is well above the threshold. Neptune's orbital acceleration is actually much greater than A0, which is why we've never noticed any deviation in the solar system. It's only when you get to the outer reaches of galaxies, where the accelerations become whisper faint, that the modification kicks in. And when it does kick in, it reproduces flat rotation curves very naturally, without dark matter, just by changing the rule. Now you might think that sounds too convenient, and it's worth being honest here. For many physicists, MOND does feel a bit like it was constructed to fit the data after the fact. Milgrom introduced it specifically to explain flat rotation curves, so reproducing flat rotation curves is not quite as impressive as if it had predicted them blind. But MOND has made predictions that go beyond what it was designed to explain, and one of them is genuinely beautiful. It's called the Baryonic Tully-Fisher Relation. The Tully-Fisher relation has been known since the late 1970s, the correlation between a galaxy's luminosity, how bright it is, and its rotation speed. Faster spinning galaxies tend to be brighter. The baryonic version, the Baryonic Tully-Fisher relation, takes this further and relates a galaxy's total baryonic mass, the mass of all its ordinary matter, not just the stars but the gas as well, to the 4th power of its flat rotation velocity. That's a tight relationship, astonishingly tight in fact, and it holds across an enormous range of galaxy sizes and types, from tiny dwarf galaxies to massive spirals. The mass, taken to the 4th power of the velocity, comes out the same. It's almost eerie. Here's what makes MOND interesting in this context. MOND predicts this relation naturally. It falls out of the mathematics almost automatically. If MOND is how gravity behaves at low accelerations, then the Baryonic Tully-Fisher relation is simply what you'd expect. No adjustable parameters, no fitting a different dark matter halo to every galaxy. The prediction follows from the theory cleanly, in the same way that the elliptical orbits of planets follow from Newton's gravity. You put in the rule, you get out the relationship. In the dark matter framework, on the other hand, this tight relationship requires explanation. The galaxy's rotation speed is set partly by its ordinary matter and partly by its dark matter halo, for the Baryonic Tully-Fisher relation. To hold as tightly as it does, the dark matter distribution would need to be very closely correlated with the ordinary matter distribution, tuned somehow to the visible stuff. That tuning is not impossible, and there are theoretical mechanisms by which it might arise from galaxy formation, but it requires some work to explain. MOND gets it for free. That is a genuine success, and it deserves to be presented as one. Give MOND its due. It is not a fringe theory proposed by someone who doesn't understand physics. Milgrom is a serious physicist. MOND has been studied carefully for more than 40 years, and in the regime of individual galaxy rotation curves, it often performs astonishingly well, sometimes better, in fact, than specific dark matter models that require you to fit the shape of a dark matter halo differently for each individual galaxy. Galaxy by galaxy, MOND can walk in and explain the rotation curve with a single parameter, A0 fixed universally. That is a real, substantive virtue. So in 1983, Milgrom offered a fork in the road. Either we accept that something invisible, some new substance we've never detected in a laboratory, makes up the bulk of the universe and holds galaxies together, or we accept that our gravity law, trusted for centuries, needs a modification at very low accelerations. Two paths, both uncomfortable in their own way, both taken seriously by real scientists. For decades, the debate ran, and neither side had a clean knockout. The rotation curves could be explained both ways. The arguments went back and forth, technical and complex, with MOND winning in some contexts, and dark matter looking more convincing in others. Neither theory could deliver the kind of clean, decisive test that would settle the matter once and for all. And then something strange happened. Something strange turned up in a patch of sky through an unusual telescope in the hands of an astronomer named Peter van Dokkum. Something that looked, at first, like a problem for everyone. But we'll come to that in a moment, because the path to that discovery runs through one more piece of evidence, one that we haven't touched yet, and that operates on a completely different scale through a completely different mechanism. Something that doesn't care about rotation curves at all, something that uses the fabric of space itself as its measuring instrument. Before we follow Zwicky's dark matter through to its strangest modern test, it's worth lingering just a little longer with what we know and what we don't. Because this is a story with an honest gap in the middle of it, and that gap deserves to be named. We said dark matter is detected only gravitationally, and we've been talking mostly about galaxy rotation curves and cluster dynamics. But there is another method, a truly beautiful one, and it provides independent confirmation that dark matter is real. General relativity tells us that mass curves space-time, and when light travels through curved space-time, it bends. A massive object between us and a distant light source will act like a lens, bending and magnifying the light of things behind it. We call this gravitational lensing. It has been observed in beautiful detail, rings and arcs of distorted background galaxies wrapped around foreground clusters, images split and stretched and multiplied by the gravity in between. The wonderful thing about gravitational lensing is that it responds to all the mass in front of it, not just the visible mass, not just the glowing stuff, but everything that has gravity. And when astronomers map the lensing in a galaxy cluster, they find far more bending than the visible matter can produce. The gravity is there. The luminous matter isn't enough to account for it. Whatever is doing the bending is abundant, distributed differently than the visible galaxies, and completely dark. This is independent of rotation curves entirely. It's a different measurement, a different technique, a different scale, and it points to the same conclusion. And then there is one case, one remarkable collision that put the two pieces, the dark matter and the ordinary matter, in visibly different places so you could see the separation with your own eyes. In a galaxy cluster called the Bullet Cluster, catalogue name 1E065756, two enormous clusters of galaxies collided and passed through each other. This happened long ago, and we observe the aftermath. When two clusters collide, the galaxies themselves, those point-like stars and gas, pass through mostly unimpeded because the space between individual stars within a galaxy is vast. But the hot gas, the diffuse cloud of ordinary baryonic matter that fills the space between galaxies and accounts for most of the cluster's ordinary mass, collides and interacts. The gas heats up to millions of degrees, glows in X-rays, and is slowed and dragged by the collision. It piles up in the middle between the two clusters like two waves of water meeting. The galaxies, meanwhile, continue on their original trajectories and exit on both sides. Now comes the crucial observation. Astronomers map the gravitational lensing of the Bullet Cluster. Where is the mass, the true total mass, the thing doing the bending? And the answer is striking. The lensing mass is concentrated on the two sides where the galaxies have moved to. It is not in the middle where the glowing X-ray gas has piled up. The gravity is where the gas isn't. The dominant mass, the thing that accounts for most of the gravity, sailed through the collision unimpeded, just like the galaxies, passing right through without slowing down. And the hot gas, the visible ordinary matter, got stuck in the middle. The two components, dark and ordinary, separated cleanly in the collision. This is about as direct a demonstration as you can get. The dominant gravitating mass does not behave like the ordinary matter. It doesn't interact in the collision. It doesn't slow down. It passes through. And MOND, being a modification of the gravity law rather than the introduction of new mass, faces a serious challenge here, because if it's just a gravity law, the gravity should be centered on the mass that's there, and in the Bullet Cluster, the visible mass is in the middle, not on the sides where the lensing says the gravity is. The gravity lives somewhere the baryons are not. The Bullet Cluster is not proof by itself. Nothing in science is. But it is a powerful, independent visual illustration of dark matter as a substance that can be spatially separated from ordinary matter. It moves differently, it lives differently, it is something distinct. So we have rotation curves, cluster dynamics going back to Zwicky in 1933, gravitational lensing, and the Bullet Cluster. That is 4 different lines of evidence from different scales using different techniques, and they all point at the same thing. An invisible, collisionless, gravitating component that outweighs ordinary matter roughly 5-to-1, and we still haven't caught a single particle of it in a laboratory. The hunt has been going on for decades. The leading particle candidates go by 2 names that have become familiar in physics circles: WIMPs and axions. WIMPs are weakly interacting massive particles. The name tells you most of what you need to know. They're heavy as particles go, and they interact through the weak nuclear force, meaning they can very occasionally bump into ordinary matter, but only very rarely. The idea is elegant because the mathematics of particle physics actually predicts particles of roughly this mass and interaction strength from other considerations, suggesting that WIMPs might not have been invented purely to explain dark matter. They might be part of a deeper theory of fundamental particles that just happens to provide dark matter as a bonus. Physicists call this the WIMP miracle. To search for them, you go underground, far underground, into mines and tunnels where the rock overhead shields you from the constant rain of cosmic rays and other background particles that would drown out any signal. You build detectors filled with ultra-pure materials, xenon, germanium, silicon, and you wait. You wait for a WIMP from the dark matter halo of the galaxy to pass through, and, just once in a very long while, interact. The recoil of an atomic nucleus, a tiny pulse of heat or light. That's what you're looking for. Experiments like Xenon and Lux Zeppelin, the latter one of the most sensitive dark matter detectors ever built, deployed deep underground, have run for years. They have become extraordinarily sensitive. They can detect individual electrons liberated in their liquid xenon targets, and they have found nothing, no confirmed signal, not a single WIMP. That is an honest result, and it deserves to be stated honestly. The most sensitive searches have come up empty. This doesn't mean dark matter isn't there. The gravitational evidence for its existence is overwhelming and comes from entirely different measurements, but it does mean that if dark matter is made of WIMPs, those WIMPs interact more weakly with ordinary matter than our most optimistic models suggested. The WIMP miracle is looking a little less miraculous with each null result. Axions are a different candidate. They were actually proposed for a completely different reason, to solve a problem in the theory of the strong nuclear force. And then people noticed that they could also be dark matter. They're much lighter than WIMPs, extraordinarily light, and they interact even more feebly. The searches for axions require a different kind of detector, one that can potentially detect the tiny electromagnetic signal that an axion might produce when it passes through a strong magnetic field. Those searches are ongoing, and they've had some interesting hints. But as of the knowledge we're working with tonight, no confirmed detection. MACHOs, massive compact halo objects, were an earlier proposal that has been largely set aside. Could dark matter just be ordinary stuff we haven't seen? Failed stars too dim to detect, or rogue black holes, or dense clouds of cold gas? These would still be made of ordinary baryons, just hard to see. The answer turns out to be no, for two reasons. First, extensive microlensing surveys. Programs called MACHO and EROS, which watched millions of stars in the Magellanic Clouds for the brief brightening that happens when a compact object passes in front of a background star, found far fewer events than MACHOs would require. The halo of the galaxy is not full of compact dark objects in the mass ranges searched. Second, and more fundamentally, Big Bang nucleosynthesis puts a ceiling on how much ordinary baryonic matter can exist in the universe. The abundance of light elements, the ratio of hydrogen to helium to deuterium produced in the first few minutes after the Big Bang, is exquisitely sensitive to the density of ordinary matter at that time. The measured abundances match a universe where ordinary matter accounts for only about 5% of the total energy, not enough to be dark matter. Whatever dark matter is, it cannot be ordinary atoms, not neutrons or protons or electrons hiding in some unlit corner. The dark matter is genuinely not ordinary stuff. It is something else, something we do not yet have a particle for. And the honest position, the intellectually careful position, is to say, we know it's there 5-1 throughout the cosmos. We do not yet know what it is. That gap between the certainty of its existence and the ignorance of its nature is where the most interesting physics is happening right now. And it's also where a strange pair of galaxies discovered in 2018 and 2019 slipped in to change the argument in a way nobody quite expected. Because so far the debate has been something like this. On one side, dark matter, an invisible substance, overwhelming in quantity, explaining rotation curves and cluster dynamics, and gravitational lensing all at once. On the other side, MOND, a modification of gravity at low accelerations, explaining rotation curves economically, predicting the Baryonic Tully-Fisher Relation beautifully. The contest seemed to favor dark matter on the large-scale evidence and the CMB, and favor MOND on the galaxy-by-galaxy detail. What neither side had was a clean test, an experiment where one theory predicted one thing, the other theory predicted the opposite, and the universe could settle it. Until, using an instrument called the Dragonfly Telephoto Array, an unusual telescope built from arrays of camera lenses designed specifically to detect extremely faint, diffuse structures, Peter van Dokkum and his collaborators found something that at first looked like a catastrophe for the dark matter camp. They found a galaxy, a real, named catalogued galaxy, NGC 1052 DF2, known informally as DF2, that appeared to contain almost no dark matter at all. And here is where things become strange. And here is where, if you're still with us, you're about to hear the punchline of everything we've been building toward. A galaxy with no dark matter sounds at first like a problem for dark matter theory. If dark matter is everywhere 5-to-1, shouldn't every galaxy have plenty of it? Finding a galaxy without it seems to suggest perhaps that it's not as universal as claimed, that the theory has a hole. But think back to what we said at the very beginning of tonight's journey, the fundamental question, the paradox that launched this whole careful walk through the evidence. Can you lose a substance? Can you lose a rule? If dark matter is a substance, a real physical thing, a component of the universe with mass and location and density, then yes. A galaxy could, in principle, have very little of it. The way a cup of coffee can have very little sugar, or a lake can be low on fish, or a star can be deficient in heavy elements, substances can be distributed unevenly. Some places have more, some places have less. In principle, some place could have almost none. But if MOND is right, if the flat rotation curves are not the effect of extra mass, but the effect of a different rule of gravity that kicks in at low accelerations, then there is no substance to lose. The rule applies everywhere, always. The way the speed of light applies everywhere, the way electromagnetism applies everywhere. You cannot have a galaxy that opts out of the rule. You cannot have a corner of the universe where gravity suddenly goes back to behaving purely Newtonian at low accelerations because the force law changed locally. Rules don't have exceptions of that kind. And a galaxy that obeys plain, unmodified Newtonian gravity, a galaxy whose stars move exactly as you'd expect from the visible matter alone, with no extra pull, no flat rotation curve behavior, nothing beyond what Newton predicts, is precisely the thing that DF2 appeared to be. Its globular clusters, those tight spherical swarms of ancient stars that orbit in a galaxy's halo, the same kind of objects Zwicky used to probe the Coma Cluster, moved slowly. Their velocity dispersion, the spread in their speeds as measured by spectroscopy, came out at roughly 8 kilometers per second. 8. To give you a sense of comparison, the stars in our own Milky Way's halo move at speeds more like 200 kilometers per second. 8 is quiet. 8 is almost still. And when you calculate how much mass is required to produce gravitational tugs capable of giving those globular clusters that gentle, unhurried motion, the answer comes out very close to the mass of the stars you can already see. No dark halo required, no invisible scaffold. The visible matter accounts for essentially all of it, which in the dark matter framework is surprising but not forbidden. A galaxy could somehow have lost its dark halo, or never gathered much of one. A substance can be absent. In the MOND framework, it's something closer to forbidden, because MOND says the gravity at those low accelerations, out in the sparse halo of a galaxy, where the pulls are gentle and faint, should be amplified beyond what Newton predicted. Always. Everywhere. With no exceptions. But DF2's globular clusters are moving at 8 kilometers per second, moving as if nothing is amplifying the gravity, moving as if Newton is just Newton, unmodified as advertised. That is not supposed to happen in MOND's universe. And DF2 itself is remarkable in another way, apart from its dynamics. It is an ultra-diffuse galaxy, vast in extent, close to the size of the Milky Way, and yet containing only about 1/200th the number of stars. Spread so thin, so gossamer faint, so transparent, that when you look at it through a telescope you can see background galaxies shining right through it. Other galaxies, far more distant, visible straight through the stellar body of DF2 as though DF2 were barely there. A ghost of a galaxy. A whisper of stars draped across a piece of sky, see-through in a way that most galaxies never are. It was discovered using the Dragonfly telephoto array, an instrument specially designed to catch exactly this kind of faint, spread-out signal that conventional telescopes tend to wash out against the sky background. Van Dokkum and his team published their findings in Nature in March of 2018. The claim was immediate and stark. Here is a galaxy with no dark matter. And because DF2 is genuinely extraordinary, because the result was extraordinary, the scientific community did what scientific communities should do with extraordinary claims. They pushed back. We'll sit with that for a moment, that beautiful transparency on a galaxy you can see through, a galaxy held together by almost nothing, sitting out there near a great elliptical called NGC 1052, drifting quietly in the dark. And then we'll follow the pushback, the scientific fight, the distance controversy that nearly erased the whole discovery. But not quite yet. For now, if you're growing sleepy, let those images settle. Zwicky in 1933 pointing at the Coma Cluster, naming a darkness that nobody believed. Milgrom in 1983 proposing that the darkness might not be there at all, that the rule might just need fixing. The bullet cluster letting you see the mass separate from the light as two enormous structures passed through each other. And DF2 see-through silent, its clusters drifting at 8 kilometers per second, behaving in a way that one of those theories simply cannot accommodate. There is something deeply peaceful about a puzzle that has been so carefully set up. Like a book where all the pieces are on the table and you can feel the shape of the answer just ahead, even if the last few pages are still to be turned. We'll turn them together, slowly. So, DF2, let's stay with it a while before we move. It deserves that. Picture the Dragonfly telephoto array. And already the name is doing something, isn't it? Dragonfly, telephoto, there's something almost tender about it, an instrument named after an insect that sees in 1,000 directions at once, built not to cut through the sky, but to gather it gently, to catch the faintest whisper of light that other telescopes simply cannot hold. Peter Van Dokkum and his collaborators designed Dragonfly specifically to find things the sky wants to keep secret. Objects so diffuse, so spread thin against the darkness that conventional instruments blur them away. Most telescopes are excellent at finding bright things. Dragonfly was made for ghosts, and NGC 1052 DF2 is, in every sense, a ghost. It is about as wide as the Milky Way, and take a moment to feel that because the Milky Way is roughly 100,000 light-years across, a genuinely enormous structure that contains something like 200 to 400 billion stars. DF2 stretches across a similar span of space, and yet it holds only about 200 million stars. That is roughly 1/200th of a typical galaxy's stellar population, scattered across a region of space that should, by rights, contain vastly more. The result is something almost paradoxical. It is a galaxy the size of a galaxy, but with nearly none of what we'd call a galaxy's substance, a vast, airy nothing, a breath held across 100,000 light-years, so faint, so diffuse, so spread out against the darkness that when Van Dokkum's team looked at DF2, they could see straight through it, not metaphorically, literally. Galaxies that lie far behind DF2, millions and millions of light-years more distant, are visible right through the galaxy itself, shining faintly through the gaps between its stars the way streetlights are visible through fog.
A galaxy so spare, so nearly empty, that the universe behind it shows through like light through a gauze curtain. There is something almost unbearably delicate about that image, if you hold it.
And scattered across this ghost galaxy like seeds dropped on snow, there are globular clusters. These are the things that told the story. Globular clusters are dense, spherical collections of stars, ancient, tightly packed, the kind of structure that forms early in a galaxy's life and tends to persist for billions of years. DF2 has them, a small population of them, and they are themselves a little unusual, somewhat brighter than typical, somewhat more luminous than you'd expect. But what mattered most for the question of dark matter was not how bright they were. It was how they were moving. Van Dokkum's team measured the velocity dispersion of those globular clusters, which is a way of saying they measured how fast the clusters were moving relative to each other, that spread of speeds that tells you how much gravity the system is working with. If there is a massive dark halo surrounding the galaxy, its gravity accelerates everything inside it, and you expect to see clusters zipping around at considerable speed. High velocity dispersion means deep gravitational well. Low velocity dispersion means shallow gravitational well, which means less total mass. The velocity dispersion Van Dokkum's team measured for DF2's globular clusters was roughly 8 kilometers per second. 8, not 80, not 800, 8. To give you a sense of scale, our own moon moves around the Earth at about a kilometer per second, and it is orbiting something the size of the Earth. Globular clusters orbiting an entire galaxy, even a relatively small one, should be moving considerably faster than that if there is a substantial dark halo involved. But 8 kilometers per second is consistent, almost precisely, uncomfortably precisely, with the gravitational pull of the stars alone, the visible matter, the stuff you can see. The stars themselves, with no additional mass required, could account for the motions Van Dokkum's team observed. The conclusion was stark and immediate. NGC 1052 DF2 has little or no dark matter halo. Its mass is accounted for by its stars. Van Dokkum and his collaborators published this in Nature in March of 2018, and the reaction, as you might imagine, was considerable. Because this was not a small claim. Saying you found a galaxy without dark matter is a bit like saying you found a river without water, given that dark matter is supposed to be the dominant gravitational ingredient in essentially all large gravitating structures. Galaxies are supposed to be embedded in dark halos. That is the prediction of the Standard Model, Lambda CDM, the framework that describes a universe of cold dark matter threaded together by dark energy. Under Lambda CDM, a galaxy the size of DF2 should be swimming in dark matter, its dark halo far more massive and far more extended than its stellar body. The dark matter should be there even if you can't see it, especially because you can't see it. And it isn't. So either DF2 is an extraordinary exception to the rule, a galaxy that somehow formed without acquiring its expected dark halo, or something is wrong with the measurement. And scientists, being scientists, were immediately and productively suspicious of the measurement. We'll come back to that suspicion. But first, let me tell you about DF4, because one ghost galaxy could be a mistake. Two is harder to explain away. The same team, Van Dokkum and his collaborators, went looking in the same general region of sky. NGC 1052 DF2 lives near a massive elliptical galaxy called NGC 1052, a large, ancient, relatively featureless ball of old stars that anchors a small galaxy group out there in the dark. And in 2019, the same group published a second result, this time in the Astrophysical Journal Letters, NGC 1052 DF4, another ultra-diffuse galaxy in the same neighborhood, another ghost. Another galaxy stretched wide across the sky, paper-thin in stellar density, so faint that it almost disappears against the background glow of the universe. And DF4, too, appeared to contain essentially no dark matter. Its globular clusters moved slowly, its internal dynamics matched its visible mass. It was, in the language of the dossier, a confirming second object, not a one-off, not a fluke of observation or a freak of measurement, but a second independent example of the same extraordinary phenomenon occurring in the same general environment near the same host elliptical. Two galaxies, both ultra-diffuse, both apparently stripped of their dark matter, both hanging near NGC 1052 like two leaves that have somehow lost their bark, still shaped like trees but missing their substance now. Here is where the story sharpens. Here is where this particular puzzle, which has been building across the evening, reveals what it was actually teaching all along. Think back to what we said about MOND, about Mordehai Milgrom's proposal from 1983, the idea that below a certain threshold of acceleration, that critical scale, A0, roughly 1.2 times 10 to the power of negative 10 meters per second squared, gravity behaves differently than Newton predicted, not because there is extra mass that we can't see, but because the law of gravity itself changes at very low accelerations. The force falls off more slowly, it stretches, it lingers, and because the outer parts of galaxies involve just that kind of very low acceleration, the stars out there at the edges feel more gravity than pure Newton would suggest, and so they orbit faster. Flat rotation curve, no dark matter required. This is the key thing to hold in mind. MOND proposes a modification to a law, to a rule, to the fundamental mathematical relationship between mass and the force of gravity. And here is the thing about rules, about laws. Rules are universal. You cannot have a galaxy where the rule applies and another galaxy right next to it where the rule doesn't apply. If MOND is correct, if the modification to gravity is a real feature of the universe at low accelerations, then every galaxy in the universe is subject to that modification. All of them, without exception. The rule is either the rule or it isn't. You cannot switch off a physical law for one galaxy and leave it on for the next one. That is not how physics works, so if DF2 and DF4 are genuinely galaxies where the inner dynamics are described perfectly well by plain Newtonian gravity, where there is no extra force, no additional gravitational reach, no flattening of the rotation curve, then MOND has a very serious problem, because MOND as a universal modification of gravity should apply to DF2, it should apply to DF4. If the acceleration felt by objects inside those galaxies falls below A0, and given how diffuse and low mass those galaxies are, much of the gravitational pull inside them might indeed be in that very low regime. Then MOND predicts they should show the extra pull. The stars and clusters should be moving faster than bare visible mass would produce. They aren't. They are moving at 8 kilometers per second, slowly, quietly, precisely as Newton, unmodified, would predict if you had only the stars and no extra force at all. A galaxy behaving like plain Newton in a regime where MOND should operate is not just an anomaly for MOND. It is, in a very precise sense, the one kind of observation that MOND as a universal rule cannot accommodate without doing something acrobatic. If the rule must apply everywhere, and the rule predicts extra gravity, and this galaxy shows no extra gravity, well, that is the experiment saying something. But dark matter, the other framework, the one where the extra mass is a real substance distributed in halos around galaxies, handles DF2 and DF4 in a completely natural and unsurprising way, because dark matter is stuff. It is a substance, and a substance is something a galaxy can have a lot of, or a little of, or in principle none of at all, depending on its history. A galaxy that missed its dark halo, or had it removed, or formed in some unusual environment that left it dark matter poor, is an entirely coherent idea within a framework where dark matter is something physical that can be accumulated or lost. A galaxy without dark matter is unusual under lambda CDM. It needs explaining, and we'll get to how it might have happened. But it is not impossible. It does not violate the theory. It is a bit like finding a lake with no fish. Lakes are supposed to have fish generally, but a lake can lose its fish. Something can happen to remove them. The lake's existence without fish does not prove that fish don't exist. It just tells you something about this particular lake's history. A universe with a modified gravity law but no dark matter, on the other hand, has no mechanism for a galaxy to behave as if the modification doesn't apply. The law either applies or it doesn't. And if DF2 and DF4 show you the law doesn't apply, or rather, that something behaves as if only ordinary Newtonian gravity is at work, you are either looking at an exception to a supposedly universal law, which is very hard to accommodate, or you are looking at a missing substance, which is exactly what the dark matter framework predicts is possible. This is the core of the argument, the rule versus the substance. You cannot lose a law, but you can lose a thing. It is, when you sit with it quietly, rather elegant. The universe ran a control experiment for us. Here, it said, here is a galaxy where the substance is absent. See what that looks like, and what it looks like is a galaxy obeying plain Newton, behaving as if nothing extraordinary is happening with gravity at all, which is exactly what you'd expect if the substance, the dark matter halo, had simply been removed. Hold that thought because it is important. But let's also hold it honestly, because this argument, clean and satisfying as it is, rests on a measurement. And the measurement was challenged. This is the part of the story that scientific reporting often skips over, and it's one of the most interesting parts. Because the discovery of DF2 as a galaxy without dark matter did not sail quietly into the textbooks. It was contested, sharply and seriously contested by serious astronomers doing careful work. The challenge came in 2019 from Ignacio Trujillo and his collaborators, including Mireia Montes and Javier Roman. And their challenge was not about the galaxy's properties per se, it was about something more fundamental and more treacherous: distance. Here is the problem. When you look at a galaxy, any galaxies in the sky, you see a patch of light. You can measure how bright it is, how wide it appears, how many stars seem to be there. But all of those are apparent properties, what you see from here. To know the actual physical properties, how intrinsically bright the galaxy is, how physically large it is, how much mass it contains, you need to know how far away it is. Because a galaxy that is very faint and very nearby might be physically the same size as a galaxy that appears somewhat brighter but is much farther away. Distance is everything. And distances to galaxies are genuinely hard to measure. There is no tape measure you can stretch across the cosmos. There are a series of what astronomers call distance indicators, observational techniques that give you a handle on how far something is. And they have different ranges of applicability and different sources of uncertainty, and they do not always agree. Van Dokkum's team had placed DF2 at roughly 19 to 20 megaparsecs. A megaparsec is about 3.26 million light-years, so 20 megaparsecs is something like 65 million light-years. That is a very long way. At that distance, DF2 has the physical size and luminosity that makes it genuinely gigantic and sparse, wide as the Milky Way, with very few stars. Trujillo, Montes, and Roman looked at the available data and argued that DF2 was in fact closer by a significant amount, roughly 13 megaparsecs rather than 20, and 13 megaparsecs changes everything. If DF2 is at 13 megaparsecs rather than 20, then it is physically smaller than Van Dokkum's team assumed. It is intrinsically less luminous. Its stars are fewer than they appear at the far distance. Its globular clusters are not as bright as they seemed. And, crucially, the total mass you'd infer from the velocity dispersion of those globular clusters changes, because the velocity dispersion measurement needs to be interpreted in the context of the galaxy's total gravitational field, which depends on how physically large and how massive the system actually is. At 13 megaparsecs, Trujillo and his collaborators argued DF2 is not so exceptional. At 13 megaparsecs, it could be a fairly ordinary galaxy with a normal dark matter content. The startling result, the lack of dark matter, might be an artifact of placing the galaxy at the wrong distance. This was not a small objection. It was a serious challenge from respected astronomers, backed by careful analysis. And for a time, it genuinely put the discovery in question. Van Dokkum's team responded by doing something elegant and methodical. They gathered 5 independent distance indicators, 5 separate techniques, each sensitive to different properties of the galaxy, each giving an independent handle on how far away DF2 actually is. And the 5 techniques they assembled included particularly powerful ones. One of them was the tip of the red giant branch method. Here is how that works. In any stellar population containing old stars, there is a well-understood point in the life of a red giant where it undergoes a dramatic brightening event called the helium flash. A moment where the star's core abruptly ignites helium fusion and the star's luminosity spikes to a specific, predictable peak before it settles into a quieter phase. That peak luminosity is the tip of the red giant branch, and it is remarkably consistent across different stellar populations. A standard candle in the language of astronomy. You observe the apparent brightness of the tip of the red giant branch. You know how intrinsically bright it should be. And the difference tells you the distance. It is one of the most reliable distance indicators available for galaxies at this kind of range. Another technique Van Dokkum's team used was surface brightness fluctuations. This one is a little counterintuitive but rather beautiful. When you look at a galaxy that is relatively nearby, you can begin to resolve individual stars. The image is granular, textured. When the galaxy is far away, the stars blend together into a smoother glow. The fluctuations average out. The image looks more uniform. The amount of granularity in the image of a galaxy is therefore a measure of its distance. The grainier it looks, the closer it is. Surface brightness fluctuations, measured carefully, give you another independent handle on how far away the galaxy is. Both of these techniques, along with 3 others, returned distances consistent with the farther estimate, the roughly 20 megaparsec distance that Van Dokkum's team had originally proposed, not 13, 20. And when 5 independent methods using different physical principles, different features of the galaxy, different parts of the observational data all point to the same answer, that is a strong case. The distance fight is not entirely settled in science. These things rarely close with perfect finality overnight, and there are still astronomers who look at the data carefully and see room for uncertainty. But the weight of the evidence, as it accumulated from multiple techniques, leaned toward the farther distance. And that meant the original result, the startling one, the galaxy with no dark matter, was not an artifact. It was real. Or at least as real as astronomy allows when the universe is 65 million light-years away and our best tools are still imperfect rulers stretched across the dark. DF2 at 20 megaparsecs is a genuine ultra-diffuse galaxy, genuinely sparse, genuinely holding its globular clusters at low velocity dispersions, genuinely lacking the massive, dark halo that the standard model says should be there. And DF4, sitting nearby, confirms the phenomenon is not unique to one object. So there are 2 galaxies, apparently without dark matter, and one of the leading alternative theories, MOND, the modified gravity idea, struggles to explain why they behave as plain Newton would predict. The rule should apply everywhere. It apparently isn't applying here. That is the argument in favor of dark matter as substance. But MOND has a defense, and it is important to hear it honestly because the external field effect, which is what MOND proponents invoke in this context, is not a desperate dodge. It is a genuine feature of how MOND works, and it reflects something true and interesting about the theory. Here is the subtlety. MOND is not a simple linear modification of gravity. It has a non-linear structure, which means that the behavior of gravity inside one system can be influenced by the external gravitational field that system is sitting in. In ordinary Newtonian gravity, this would not matter in the same way. You can simply separate the internal dynamics from the external field and analyze them independently. But in MOND, the external field and the internal field interact in a specific way, and a sufficiently strong external field can suppress the MOND modification inside a smaller embedded system. This is called the external field effect. And the relevance to DF2 is immediate and precise. DF2 and DF4 are not floating freely in empty space. They are sitting near NGC 1052, the large, massive elliptical galaxy that anchors the group. NGC 1052 is a substantial gravitational presence, and DF2 and DF4 are embedded to some extent in its gravitational field. Under MOND's external field effect, if the external gravitational field from NGC 1052 is strong enough relative to the internal accelerations within DF2, the MOND modification inside DF2 could be suppressed. DF2 could end up behaving like a plain Newtonian system. Not because MOND doesn't apply to it in principle, but because the external field has drowned out the internal MOND signature. This is not an ad hoc rescue. The external field effect is a mathematically genuine prediction of MOND's non-linear structure, not a patch invented after the fact to explain away an inconvenient result. MOND researchers had discussed the EFE long before DF2 was discovered, and they can in principle calculate what magnitude of external field would be needed to suppress MOND inside DF2 and ask whether NGC 1052's field is plausibly of that magnitude at DF2's position. So MOND has a real escape route, a narrow one perhaps, a route that depends sensitively on the precise distance of DF2 from NGC 1052, which is again entangled with the contested distance to DF2 itself, and on the precise mass of NGC 1052 and how its gravitational influence falls off with position. If the geometry is right, MOND can accommodate DF2 without internal contradiction. But here is the honest weighing. The external field effect, while real within MOND's framework, requires a specific set of conditions to work. Conditions that depend on numbers that are themselves uncertain. The closer distance would help MOND here, the farther distance makes it harder. And for the EFE explanation to fully cover both DF2 and DF4 in the same general region, both galaxies need to be in exactly the right configuration relative to NGC 1052. The more conditions you need to specify, the more your theory is starting to explain particular cases rather than predict them, and the less economical it becomes. The dark matter interpretation, by contrast, requires no such fine-tuning. Under lambda CDM, DF2 and DF4 are galaxies that lost their dark matter. There is a natural physical mechanism for that, a mechanism the standard model itself contains. And that mechanism does not depend on precise positioning relative to a neighbor or on a contested distance estimate. It simply requires that the dark halo was separated from the stellar body at some point in the galaxy's past. This is the honest comparison. MOND can explain the observations, but the explanation requires specific conditions and careful geometry. The dark matter interpretation explains the observations naturally without needing to invoke any additional parameter. In science, when two frameworks can both accommodate a result, but one requires more special pleading than the other, we generally find the simpler accommodation more compelling, even if we don't rule the other one out entirely. So there you have the distance fight and the external field effect, laid out as fairly as I can manage. The discovery was challenged. The challenges raised a real scientific concern. The original team responded with 5 independent distance measurements that largely vindicated their analysis. And MOND's defense, while theoretically coherent, requires conditions that become less comfortable as the evidence accumulates. The dark matter interpretation is the cleaner reading of the data. But we should also ask the question that the dark matter framework itself must answer. If DF2 and DF4 are embedded in a dark matter universe, if the standard model is correct, then where did their dark matter go? It isn't enough to say it was removed. You have to have a mechanism, you have to have a story, and fortunately there is one. It involves tidal stripping. Here is the picture. Galaxies interact. They pass through each other, fall toward each other, collide with each other in slow, cosmic dances that unfold over hundreds of millions of years. And when 2 galaxies interact, their gravitational forces compete for the material they contain. Loosely bound material, the stuff at the edges, the outer halo, the most diffuse layers of the galaxy, is the most vulnerable. It can be stripped away by the gravitational pull of a nearby or passing companion, stretched out into tidal streams, redistributed into the surrounding space. The dark halo of a galaxy is, in this sense, the most vulnerable part of all. It is enormous, much larger in physical extent than the luminous stellar body. It is not tightly bound, its material is diffuse and widely spread, and crucially, dark matter is collisionless, and it does not bump into other dark matter the way gas clouds collide and heat up. When galaxies interact, the gas slows down, compresses, can get left behind in the center of a collision. But dark matter passes through dark matter smoothly, responding only to gravity, and it can be pulled cleanly away from the stellar body if the geometry of the encounter is right. The stellar body of a galaxy, by contrast, is much more compact, much more tightly bound. The stars are in the deep part of the gravitational well. They are much harder to strip. In a sufficiently energetic interaction, a close passage, a high-speed flyby, a collision with another system, it is entirely plausible to strip the dark halo away while leaving the stellar body more or less intact. The loosely bound outer layers of dark matter get peeled off, redistributed into the surrounding space or captured by the larger system, and the galaxy is left as a bare stellar body with no dark halo. An ultra-diffuse ghost, still spread wide across space where its dark matter used to scaffold it, but now held together only by its own modest stellar gravity. There is a proposed origin story for DF2 and DF4 that astronomers call, evocatively, the bullet dwarf scenario. In this picture, a high-speed collision between a smaller and a larger system in the NGC 1052 group, a bullet-like encounter where one galaxy passed through another at high velocity, could have separated the dark matter from the stars in the smaller system. And not just for one galaxy. A whole trail of dark matter-poor dwarf galaxies might mark the aftermath of such a collision, strung out along the trajectory like beads on a wire, each one a small system that lost its dark halo in the encounter. The suggestion is that DF2 and DF4 might both be remnants of this kind of event, that they are not just unusual galaxies, but fossils of a specific ancient collision, cosmic debris made from the separation of dark matter from starlight. They are evidence, in this reading, not just that dark matter can be removed from a galaxy, but that it can be removed precisely because it is a substance that is physically separable from the matter we see. Because it is a halo, a cloud, a structure that gravity can grab and pull away from the stellar body it surrounded. And if that is true, if tidal stripping can do this, if the bullet dwarf collision produced both DF2 and DF4 and perhaps other ultra-diffuse galaxies in the same region, then every element of the observation confirms the substance picture. The dark matter was there. It was removed by a physical process. The stellar remnant is what's left, and the ghost galaxy, transparent and slow, drifting near NGC 1052 with its quietly wandering globular clusters, is the universe showing us that dark matter is a thing that can be taken away. You cannot take away a law of physics and leave the rest behind. But you can take away a halo. The rule versus substance distinction played out in two ghostly, see-through galaxies 65 million light-years from here is about as clean an experimental discriminator as cosmology tends to provide. The universe rarely offers you a situation where one theory says this cannot happen and another says this is exactly what you'd expect. Usually the differences are more subtle, more tangled in uncertainty, harder to extract. But here, in these two spare, faint, improbable objects discovered by a telescope named after a dragonfly, the universe gave astronomers something almost like a clean answer. And the answer looks more like substance than rule. Somewhere in the NGC 1052 group, if the bullet dwarf picture is right, there may be a trail of these stripped remnants, small galaxies drained of their dark matter like clothes shed in a hurry, each one confirming that the dark halo is a separable, physical, removable thing. Whether that specific scenario, the precise geometry, the particular collision, is confirmed in all its details is still something astronomers are working through. But the mechanism is real, the physics is sound, and the pattern in the NGC 1052 group is consistent with it. So DF2 sits at the center of the story, not as a problem for dark matter, as a gift, as the control experiment the universe set up for us, showing us what a galaxy looks like when the dark matter has been removed, which is to say, when it is simply absent, when only the stars remain, when Newton's unmodified gravity is all there is. And what that looks like is globular clusters drifting at 8 kilometers per second, slow and quiet, describing with their gentle orbital wandering the shape of a gravitational well made only of stars. That is what a galaxy without dark matter looks like. And the fact that it looks like a special case, not like a galaxy where the rule has been bent, but like a galaxy where the substance is missing, is the observation that tells you which story is right. You can lose a thing, you cannot lose a rule. 8 kilometers per second in the outer reaches of a ghost galaxy 65 million light-years away. Quiet, slow, telling us something true. We are not done though, because DF2 and DF4, for all their elegance, are two galaxies, and science does not rest on two galaxies. The case for dark matter is far older and far broader than any single pair of observations, however striking. The independent pillars of evidence stretch from the earliest moments of the universe's history all the way to the present, and they all point to the same missing thing, the same invisible scaffolding that holds the cosmos together. That is where we are going next. The bullet cluster, where gravity and light went their separate ways. The cosmic microwave background, where the fingerprint of dark matter was written into the oldest light in the universe. 380,000 years after the Big Bang. The great cosmic web, the filaments and halos that dark matter built so that stars could form at all. And the honest, open, frustrating gap at the heart of it all, the experiments searching for the particle itself, the underground detectors listening in the dark, and the silence they keep returning with. But let those thoughts settle for now. If you are fading, if the edges of the room are going soft, if the words are drifting just a little, that is perfectly fine. The galaxies will be here. DF2, transparent as gauze, DF4, its quiet companion. Globular clusters moving at 8 kilometers per second, slower than the speed of sound on a summer day, drifting across a gravitational well made only of stars. No law broken, No substance present, just starlight, held by starlight, in the dark. So let us talk about MOND's last clever escape route, because the defenders of modified gravity did not simply fold when DF2 was announced. They had a card to play, a genuine, technically serious card, and it deserves a fair hearing before we weigh it against everything else. The argument goes like this. MOND is not quite the simple story it first appears. When Mordehai Milgrom proposed it in 1983, he was not just sketching a line through some data points and calling it physics. The theory has a real internal structure, and one of its less advertised features is something called the external field effect. The external field effect, the EFE, as it is known, arises because MOND is what physicists call a nonlinear theory. In ordinary Newtonian gravity, you can think about a small galaxy in complete isolation, calculate its internal dynamics, and ignore whatever large structures might be sitting nearby. The equations are separable. The neighborhood does not reach inside, but in MOND, the gravitational field of a larger surrounding system can bleed into a smaller one. If a little galaxy is moving through the deep gravitational field of a massive neighbor, that external field can suppress the MOND behavior inside the small galaxy. It can effectively push the small galaxy's internal accelerations back up above the critical threshold A0, the scale at which MOND's modification kicks in, and return the galaxy's internal dynamics to something that looks, to a very good approximation, like plain Newtonian gravity. The environment, in other words, can reach in and change the rules. And here is why that matters for DF2 and DF4. Both of those ultra-diffuse galaxies live near a large, luminous, massive elliptical galaxy called NGC 1052. NGC 1052 is a real and powerful gravitational presence in their neighborhood. It is not a background object, not a coincidence of position on the sky. It is close enough and massive enough to potentially dominate the external field environment of its diffuse little companions. So the MOND defenders made a real argument. Perhaps DF2's internal gravity feels ordinary Newtonian because NGC 1052's external field is washing out the MOND regime. Perhaps the galaxy is not actually dark matter deficient in any meaningful sense. Perhaps it simply lives in the wrong neighborhood for MOND to show its hand, and we have been fooled into thinking we are looking at a dark matter absence when really we are looking at the external field effect wearing a mask. This is not a desperate excuse. The external field effect is a real, predicted consequence of the theory. It was not invented after DF2 was found. It follows from the non-linear structure of MOND's mathematics. And there are other galaxies where the EFE has been invoked to explain behavior that plain MOND would not predict, with some success. The argument is, by the standards of scientific debate, a legitimate one. You should not dismiss it, and honest astronomers do not. But here is where the weight of the evidence starts to pull the scales in one direction. The external field effect, to actually work, to actually suppress the internal MOND dynamics of DF2, requires that the external field from NGC 1052 be strong enough relative to DF2's own internal field to dominate. And that calculation depends quite sensitively on how far DF2 actually is from NGC 1052. Not just how far DF2 is from us, but the three-dimensional separation between the two objects. And that in turn comes back to the very distance controversy we covered before. Ignacio Trujillo and his collaborators, who argued that DF2 was closer to us than Van Dokkum's team claimed, closer by nearly half, around 13 megaparsecs rather than 19 or 20, naturally arrived at a three-dimensional geometry that made the EFE more plausible. A closer DF2, sitting more cozily within NGC 1052's gravitational reach, made the external field argument easier to sustain. But Van Dokkum's team, having assembled 5 independent distance indicators, the tip of the red giant branch method, surface brightness fluctuations, and 3 others, and finding them converge on the larger distance placed DF2 in a location where the EFE calculation becomes considerably more strained. The external field from NGC 1052 is weaker at greater separations, and at 20 megaparsecs, the case that it is sufficient to suppress MOND internally requires some careful assumptions. The EFE rebuttal, in other words, leans heavily on the shorter distance, and the shorter distance is the contested one. There is something almost elegant about the way the two arguments entangle. The EFE is MOND's best answer to DF2, but the EFE's best version of itself requires the distance to be closer than the 5-ruler consensus suggests. The distance debate and the EFE debate are not separate fights. They are the same fight seen from two angles. And as things stand, the weight of the independent evidence on distance lands on the side of the farther number, which makes the EFE explanation harder to sustain cleanly. Not impossible, but harder. And even if we set distance aside for a moment and granted the EFE its most favorable reading, even if we said, all right, NGC 1052's field is strong enough to suppress MOND in DF2's interior, we are left with something that should give us pause. The EFE makes DF2 look Newtonian. But what the EFE cannot do is make a galaxy physically lose its dark matter. In a MOND framework, dark matter was never really there to begin with. The EFE is just an explanation for why the modified gravity looks ordinary in this particular corner of the universe. So the EFE, at its best, saves MOND from contradiction by making the galaxy look like it has no excess gravity, but it does so by invoking a special environmental circumstance, a lucky alignment with a massive neighbor that conveniently produces exactly the signature a dark matter-free galaxy would show. It starts to acquire the faint flavor of a post-hoc rescue. Not a wrong rescue, not a dishonest one, but a rescue that requires progressively more specific assumptions about distance and geometry to sustain. The dark matter interpretation requires no such rescue. In that picture, DF2 and DF4 simply lost their dark matter halos through a physical process we can calculate and simulate. They are not special environments where a law mysteriously softens. They are ordinary places where a substance is absent, and that distinction, law versus substance, is the whole of the argument. Which brings us to the mechanism. If dark matter is a thing, a real material component that galaxies can have more or less of, then it must be possible to physically remove it from a galaxy under the right circumstances. And in fact, we know of a process that does exactly this. It is called tidal stripping. Think of tidal stripping this way. You have a galaxy, a system of stars, gas, and a dark matter halo. The stars are tightly bound. They are packed into a relatively dense, luminous disk or sphere, held together not just by gravity, but by their own internal dynamics, billions of years of orbiting and interacting. The dark matter halo is something quite different. It is diffuse. It extends far beyond the visible stars, often several times further. It is loosely bound at its edges. And crucially, dark matter does not interact with itself or with ordinary matter through any force except gravity. It is what physicists call collisionless. It does not clump up when it meets other dark matter. It does not heat up or slow down through friction or compress. It just passes. Now imagine what happens when a galaxy undergoes a close encounter, a high-speed flyby with another galaxy, or a collision in a dense group of galaxies. The stars, tightly packed at the center, are held firmly. They survive the encounter largely intact. But the dark matter halo, extended and loosely bound at its edges, feels the tidal forces of the passing or colliding system far more strongly at large radii. Tidal forces, remember, are differential gravity, the difference in the gravitational pull across an extended object. The outer parts of the halo, furthest from the galaxy's center, experience a different gravitational tug than the inner parts, and that difference can overwhelm the halo's self-gravity. Material at the edges gets stripped away, peeled off, and lost to the surrounding space or captured by the larger passing system. The result is a galaxy that has been shorn of its dark matter envelope. Its stars survive, its inner structure is mostly intact. But the halo, the invisible scaffolding that accounted for the bulk of its mass, has been pulled away and dispersed. What is left behind is something that looks dynamically like a galaxy where the dark matter never existed. Its globular clusters drift slowly. Its rotation curve does not need to be flat because there is no extra mass pulling on it. It behaves by every measurement as though its visible matter is essentially all it has. There is a proposed scenario for exactly how DF2 and DF4 came to be this way. It involves what has been described as a bullet dwarf collision, a high-speed encounter in the NGC 1052 galaxy group, analogous in spirit, if not in scale, to the famous bullet cluster. In this picture, a gas-rich dwarf galaxy passed through or past a larger system at high velocity. The loosely bound dark matter halo was stripped during the passage and left behind, while the dense core of stars, the future DF2, the future DF4, continued on its trajectory. The dark matter did not vanish. It was not destroyed. It is still out there somewhere, scattered into the surrounding group, perhaps contributing to the diffuse dark matter that fills the space between galaxies in the NGC 1052 system, and the trail of ultra-diffuse dark matter-poor galaxies along a particular stretch of sky near NGC 1052 is consistent with exactly this kind of event. A sequence of objects left behind by a violent encounter, like shells from a long-ago collision, still expanding through the group. This is the part that should feel deeply satisfying, if you are still awake enough to feel it. Because what the tidal stripping scenario does is not just explain how DF2 lost its dark matter. It tells us something about the nature of dark matter itself. If dark matter could not be stripped, if it were entangled with the stars through forces beyond gravity, if it stuck to baryonic matter, the way paint sticks to a wall, then you could not create a dark matter-free galaxy through a close encounter. The fact that you apparently can means dark matter is a collisionless gravitating fluid that is physically separable from the stellar matter it ordinarily accompanies. You can lose it. You can strip it away. You can create a galaxy without it. And the existence of that galaxy, sitting there in the NGC 1052 group, transparent as gauze 8 kilometers per second, is the fingerprint of a substance that was present and then removed, not a law that was modified, not a rule that bent in one direction and not another. A thing, a real physical component of the universe, as removable as water from a sponge. A modified law cannot be removed. You cannot strip away MOND from a galaxy. You cannot perform a tidal interaction that leaves behind ordinary Newtonian gravity and carries the Mondian modification off into space. The law either applies or it does not. If it does not apply in DF2, if DF2 genuinely obeys plain Newton, then either the law has an exception which contradicts the theory's foundations, or there is a special environmental explanation like the EFE, which we have already weighed. But dark matter as a substance can simply be gone. And a galaxy with no dark matter is exactly as possible in the dark matter framework as a swimming pool with no water is in ordinary experience. Strange, notable, worthy of investigation, but not the least bit theoretically forbidden. Now, two galaxies, however striking, should not be the whole of the case, and they are not. The evidence for dark matter runs far deeper than DF2 and DF4, and it comes from places so different, so entirely independent of rotation curves and ultra-diffuse galaxies, that the convergence itself becomes one of the most powerful arguments. Let us move through the others slowly. The The Bullet Cluster. Its official designation is 1E065756. It is a system of two galaxy clusters that collided long ago. Two vast collections of galaxies, hot gas and dark matter that pass through each other at enormous velocity. When you observe it today, you are seeing the aftermath of that collision, and the aftermath is a kind of natural laboratory that gravity and astrophysics built for us without being asked. Here is what happened, as best we understand it. Each cluster contains three main components: the individual galaxies themselves, the hot X-ray emitting gas that fills the space between them, and the dark matter halos that surround everything. When the two clusters collided, the galaxies, those discrete, compact objects, passed through each other largely unimpeded, the way two swarms of bees would pass through each other, with most individuals never directly meeting. The galaxies are small compared to the space between them. Collisions between individual galaxies are rare at cluster crossing velocities, so the galaxy populations of the two clusters sailed through. The dark matter halos did the same thing for the same essential reason. Dark matter is collisionless. It does not slam into itself or into ordinary matter through any force except gravity, and so the dark matter from one cluster passed through the dark matter of the other, like two ghosts walking through the same wall. The hot gas was different. The gas, the intracluster medium, the hot plasma, that is actually the dominant component of ordinary matter in a galaxy cluster. The gas is not collisionless, it is a fluid. When the two clouds of plasma slammed together at the speeds of a cluster collision, they interacted electromagnetically. They compressed, they heated, they generated shock waves. They slowed down and accumulated near the center of the collision, lagging behind the galaxies and the dark matter, piling up in the space between where the two clusters used to be. The Chandra X-ray Observatory captured this beautifully, a glowing arc of hot gas, the most ordinary matter in the system, smeared and slowed in the middle, like two waves colliding in a bathtub and piling up at the point of impact. Now here is the key observation. Gravitational lensing, the bending of background light by the mass in the foreground, tells you where the mass actually is, not where the gas is, not where the galaxies are, where the mass is. And in the Bullet Cluster, the mass is not where the gas is. The lensing signal shows two distinct mass concentrations, one on each side of the collision, offset from the hot gas that is glowing in the middle. The gravity passed through the collision. The ordinary matter did not. The gravity is where the collisionless stuff went. The gas is where the fluid that got slowed is. And the only way to make sense of that picture, the only consistent explanation for why the gravity and the gas have separated, why the mass and the light are in different places, is to say that most of the mass in those clusters is not the gas, not the galaxies, not any ordinary matter at all. It is something that behaves exactly as dark matter behaves, collisionless, gravitationally dominant, and utterly indifferent to electromagnetic interactions. The Bullet Cluster did not set out to test dark matter, it just ran the experiment, and the result was not ambiguous. MOND, it should be said, has real difficulty with the Bullet Cluster. The lensing mass that is offset from the gas is still more mass than the stars, and gas in those clusters can account for, even with MOND's modified gravity applied. To make MOND work in the Bullet Cluster, you need to add additional mass anyway, with some amount of undetected ordinary matter, perhaps in the form of sterile neutrinos or some other baryonic reservoir, to fill the gap, which means MOND in the cluster regime does not actually eliminate invisible matter. It just relocates the problem. And then there is the evidence from the very beginning of the universe. The cosmic microwave background, the CMB, is the oldest light we can observe. It was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, for the first time. Before that moment, the universe was a hot, opaque plasma, and light could not travel freely through it. After that moment, the universe became transparent, and photons streamed outward in every direction. Those photons have been traveling ever since, cooling as the universe expanded, and today they arrive at our detectors as a faint bath of microwave radiation, filling the entire sky at a temperature of about 2.7 degrees above absolute zero. Cold, uniform, ancient, but not perfectly uniform. When you map the CMB with enough precision, and instruments like the Planck satellite, whose full mission data were released through 2018, have done this with extraordinary precision, you find tiny variations in temperature across the sky, regions slightly warmer and regions slightly cooler by about 1 part in 100,000. These fluctuations are not noise, they are signal. They are the frozen record of something called baryon acoustic oscillations. Sound waves that propagated through the hot plasma of the early universe for those first 380,000 years, driven by the interplay between radiation pressure pushing outward and gravity pulling inward. The photons kept pushing the ordinary matter outward in expanding shells. Gravity kept trying to pull it back together. The result was a series of oscillations, acoustic waves in the cosmic plasma. And when the universe became transparent, those waves froze in place, imprinted on the pattern of the CMB as a series of peaks and troughs in the temperature spectrum. Now here is the thing. The height, the position, and particularly the relative heights of those peaks carry information, precise, quantitative information, about the composition of the universe. The first peak tells you about the total density of everything that gravitates. The second peak tells you specifically about the density of ordinary baryonic matter, protons, neutrons, electrons, everything that has ever appeared in a chemistry textbook. The ratio of the first peak to the second peak is exquisitely sensitive to how much dark matter the universe contains. And when you do the fitting, when you ask, what combination of ordinary matter, and dark energy produces the pattern of peaks that Planck measured, you get a universe that is approximately 5% ordinary matter, 27% dark matter, and 68% dark energy, consistent with other independent methods. The dark matter fraction is not a guess. It is not a parameter that someone chose because it looked convenient. It is what the data require precisely from observations of a pattern written into the oldest light in existence, 380,000 years after the universe began. And there is something important to emphasize here. The CMB evidence is completely independent of galaxy rotation curves. It has nothing to do with Vera, Rubin and Kent Ford and Andromeda. It has nothing to do with DF2 or DF4 or the NGC 1052 group. It comes from a different epoch of cosmic history, observed with a different instrument, using different physics, analyzing a different kind of signal, and it arrives at the same conclusion. Something non-baryonic, non-luminous, gravitationally dominant is present in the universe in large quantities. The agreement between evidence streams from such entirely different places is not what coincidences look like. It is what a real thing looks like. Dark matter is also, in a very literal sense, the reason you exist. The universe after the Big Bang was almost perfectly uniform. The matter, both ordinary and dark, and was spread through space with only the tiniest density variations, those 1 part in 100,000 fluctuations we see frozen in the CMB. Left to their own devices, those tiny fluctuations would need to grow. Gravity would need to draw matter into denser regions, seeding the formation of galaxies, stars, and everything else. But ordinary matter alone could not do this fast enough. In the early universe, ordinary matter was tightly coupled to radiation, to the photons themselves, through electromagnetic interactions. Wherever ordinary matter tried to clump, radiation pressure pushed it back out again. The gas was trapped by the light. Dark matter was not. Dark matter decoupled from radiation essentially at the beginning because it does not interact electromagnetically. It was free to start clumping under its own gravity long before ordinary matter could, and so dark matter got a head start. It began falling into its own density peaks, building up the first gravitational scaffolding, the early seeds of what would become the cosmic web, the great network of filaments and sheets and voids that large-scale structure surveys have since mapped. By the time ordinary matter was finally free to move, when the CMB photons streamed away and the gas was liberated, there were already dark matter halos waiting, pre-built gravitational wells, and the gas fell into them. The gas that fell into those halos cooled, compressed, and eventually formed stars. The first stars formed, galaxies assembled around dark matter scaffolding. Generations of stars lived and died, forging the heavy elements. And eventually, one particular star in one particular galaxy had, around it, a rocky planet where the chemistry got interesting. Simulations of cosmic structure formation, models with names like the Millennium Simulation, make this vivid. When you run a simulation of the universe using only ordinary matter, the structures that form are wrong. The filaments are too thin, the halos too sparse, the galaxies too late. When you add dark matter in the proportions the CMB requires, the cosmic web that grows looks like the universe we actually observe. The right abundance of galaxy clusters, the right large-scale distribution, the right timing. Dark matter is not just a fix for rotation curves, it is the explanation for why any galaxy exists at all, including the one that contains you. And yet, for all of this, the rotation curves, the bullet cluster, the CMB peaks, the structure formation, the two dark matter-free galaxies that prove the substance is separable, for all of it, we have not caught a single dark matter particle in a laboratory. The leading particle candidates have been searched for with extraordinary care. WIMPs, weakly interacting massive particles, were for decades the most theoretically favored candidates. They arise naturally from certain extensions of the standard model of particle physics. They would have been produced in the right abundance in the early universe, and they would interact with ordinary matter through the weak nuclear force, weakly, rarely, but not never. If you build a detector large enough and sensitive enough and shield it from other particles well enough, a WIMP passing through should occasionally scatter off an atomic nucleus and leave a detectable recoil. Experiments have been doing this. Underground laboratories, shielded from cosmic rays by kilometers of rock, filled with large volumes of liquid xenon cooled to cryogenic temperatures, listening for the faintest nuclear recoil signals. The LX Zeppelin detector, the current flagship of this experimental program, uses tens of tons of liquid xenon buried underground with backgrounds reduced to extraordinary levels, and the silence it returns is increasingly informative. The absence of a signal does not mean WIMPs do not exist, but it does mean that if they do exist, they interact even more weakly than the most optimistic estimates predicted, or they are heavier or lighter than the ranges that have been most thoroughly searched. Axions are another serious candidate, much lighter than WIMPs, arising from a different theoretical context and requiring entirely different detection strategies. They too are being searched for with experiments using strong magnetic fields and resonant cavities tuned to the frequency at which axion photon conversion might occur. No detection yet. And there is an older story worth remembering, now that we are being honest about what we do and do not know. For a while, one of the candidate explanations for missing mass was simply ordinary matter that we had not found yet. Dim stars, burned out stellar remnants, massive black holes, compact objects that do not shine. These were called MACOs, massive astrophysical compact halo objects. If enough of them existed in galaxy halos, perhaps the missing mass, could be accounted for without any exotic new particles. Surveys called MACHO and EROS looked for these objects through gravitational microlensing, the brief brightening of a background star when a compact foreground object passes in front of it. Those surveys found some MACHOs, but far too few to account for the bulk of the missing mass. And a separate, independent constraint seals the argument. Big Bang nucleosynthesis, the physics of how the light elements hydrogen, helium, and lithium were forged in the first few minutes after the Big Bang, is highly sensitive to the total density of ordinary baryonic matter. When you calculate how much ordinary matter the universe produced in those first minutes, you get a number that is far smaller than the total matter density required by the CMB and the large-scale structure. The shortfall cannot be made up with dim stars or black holes. They are ordinary matter, and there simply is not enough ordinary matter, however you arrange it, to fill the gap. The missing mass must be non-baryonic, genuinely new physics, genuinely a different kind of substance from anything in the periodic table. So here we are. The evidence for dark matter arrives from 5 distinct directions: the rotation curves of individual galaxies, the dynamics of galaxy clusters, the gravitational lensing in systems like the Bullet Cluster, the acoustic peaks frozen into the oldest light in the universe, and the very fact that large-scale cosmic structure exists as it does. They do not all have the same level of certainty. Some measurements are more contested than others. The distance to DF2 is genuinely uncertain in a way that the CMB is not. The precise behavior of the EFE depends on assumptions that the microlensing ruled-out case for MACHOs does not. But the 5 streams of evidence are independent of each other, and they converge. That convergence is the argument. Not one river, but 5 rivers arriving at the same sea. And dark matter's particle identity remains honestly a mystery. The underground detectors are listening and hearing nothing. The particle accelerators have not produced a WIMP. The Axion searches continue at the frontier of experimental sensitivity. This is not a failure of the idea, that the gravitational evidence is not shaken by the silence of the detectors, because the gravitational evidence rests on different physics entirely. But it is a genuine open question, perhaps the deepest open question in physics today. We know something is there. We do not know what it is made of. We know its gravitational properties. We do not know its particle properties. We can calculate its abundance with precision. We cannot hold a piece of it in our hands. Knowing that something exists and not knowing what it fundamentally is, that is not a comfortable position, but it is an honest one. And science, when it is working well, is always willing to sit in that discomfort rather than replace a real mystery with a false certainty. Let that sit for a moment. The universe is, by mass, mostly made of something we cannot see, cannot touch, and cannot identify at the particle level. Everything you have ever seen, every person, every planet, every glowing star in every galaxy, in every image ever taken, adds up to about 5%. 5 in 100. The rest is dark matter, dark energy, and the quiet strangeness of a cosmos that did not ask our permission before deciding what to be made of. And yet, and this is the thing that should stay with you if nothing else does, we know it is there. Not because someone decided it would be tidy, not because theorists needed a parameter to adjust, but because the universe told us. It told us in the arms of spiral galaxies spinning too fast. It told us in the velocity dispersion of a galaxy cluster in 1933, measured by a man named Fritz Zwicky, whose colleagues were not yet ready to believe him. It told us in the patient work of Vera Rubin and Kent Ford, turning a spectrograph toward one galaxy after another, watching the rotation curves flatten at radii where they had no business being flat. It told us in the glow of 2 colliding galaxy clusters where the gravity and the light went different ways. It told us in the delicate pattern of peaks in the oldest light in the universe. And then, quietly, in 2018, it told us one more time, in a galaxy so spare and transparent that background galaxies shine right through it, with globular clusters drifting at 8 kilometers per second, slower than the speed of sound, tracing a gravitational field made of almost nothing but stars. You cannot lose a law of physics. You cannot strip a force modification away from a galaxy with a tidal encounter. You cannot hold a controlled experiment where the modification is present in 1,000 galaxies and absent in 2, but you can lose a substance. You can have a galaxy that was once enshrouded in a dark matter halo, encountered something larger and faster, and had that halo peeled away in the tidal violence of the passage, leaving behind a stellar body moving through space, no longer weighed down by the invisible thing that had accompanied it for billions of years. DF2 and DF4 are not evidence against dark matter. They are evidence of dark matter's nature, that it is a thing, separable and losable, a material component of the universe that galaxies can keep or have taken away. The control experiment the universe ran for us was not, here is a galaxy where dark matter does not exist. It was, here is a galaxy where dark matter used to be, and here is what is left when you take it away. The two are different statements. Only one of them points toward a missing substance, somewhere out there right now, and the distance from you to it does not change what is true about it. There is a galaxy about the size of our own Milky Way, stretched across a swathe of sky so faint that you cannot see it with the naked eye or an ordinary telescope. It took the light-gathering sensitivity of the Dragonfly telephoto array, an instrument designed specifically to catch the very faintest surfaces of galaxies, to pull it out of the dark. It is called DF2, or more precisely NGC 1052 DF2, and it sits roughly 19 or 20 million light-years from where you are lying now. Behind it, further galaxies glow faintly through it, the way stars shimmer through the edge of a fog bank. Inside it, about 10 globular clusters orbit at speeds slow enough that we can measure their velocity dispersion at roughly 8 kilometers per second. And from that number, from that drifting, quiet motion, we can calculate that this galaxy's mass is essentially just its stars. No halo, no invisible envelope, no 5-to-1 overbalance of darkness to light, just starlight weighing itself. And that galaxy, transparent as gauze, nearly empty, sitting in the outskirts of the NGC 1052 group. That galaxy is one of the clearest arguments for dark matter's reality that the universe has ever produced. We have come a long way tonight. From the outer arms of Andromeda, measured in the 1970s by Vera, Rubin and Kent Ford, with a spectrograph patient enough to reveal what physics was not supposed to allow, through Fritz Zwicky's 1933 calculation at the Coma Cluster, arriving 40 years before anyone was ready to take it seriously, through the modified gravity proposal of Mordehai Milgrom, who in 1983 asked whether the anomaly might be in the law of gravity itself rather than in the inventory of mass, and whose idea is serious enough and productive enough to deserve honest engagement rather than dismissal. Through the Bullet Cluster, where two colliding galaxy clusters separated their components so cleanly that a child could point to the image and say, "Look, the gravity is over there and the light is over here." Through the frozen pattern of the cosmic microwave background, the Planck satellite's map of a universe 380,000 years old, where the relative heights of acoustic peaks encode the composition of everything that exists. Through the question of how structure ever formed at all, how the filaments of the cosmic web were woven, why there are galaxies at any particular address in the universe, and the answer every time requiring the same invisible scaffolding. And through the honest silence of the underground detectors, the liquid xenon waiting in the dark for a WIMP that has not yet announced itself, the Axion searches tuned to frequencies where the signal might one day appear. Wherever you are listening from tonight, whatever window frames, whatever piece of the night sky above you, whatever lamp is still softly lit, whatever blanket is pulled close, I want you to consider this. Right now, passing through you are dark matter particles, not metaphorically, not approximately. The dark matter halo of the Milky Way extends through the entire volume of the galaxy, and you are inside it, and the density of dark matter in the local neighborhood of the solar system, small by cosmic standards but not zero, means that there is dark matter moving through this room, through this building, through you, right now, on its way to wherever dark matter goes when it is not being looked for. You cannot feel it. No part of your body is sensitive to it. It does not scatter off your atoms in any way you could register. It passes through you the way the neutrinos from the sun pass through you, by the billions per second, noticed by nothing, leaving no trace. And yet it is part of the universe you are made of. You live inside it. The galaxy you belong to is shaped by it, held by it, would not have formed without it. The stars you cannot see tonight because the sky is too bright or the clouds are too thick, or you are inside with your eyes closed, those stars are outnumbered 5-1 by something that does not shine at all. 5-1. For every gram of ordinary matter in the universe, every proton, every neutron, every electron, every atom of every element that has ever appeared in a textbook or been touched by a human hand, there are roughly 5 grams of dark matter, invisible, structureless as far as we know, patient, gravitationally sovereign. The universe is not mostly made of the things we are made of. We are the minority component of a cosmos that built its web, wove its filaments, seeded its galaxies, and set the whole vast structure in motion, mostly in the dark. That is a strange and beautiful thing to carry into sleep. I asked at the beginning of tonight where you are listening from, and I meant it as a real question, not a formality, but a genuine curiosity, because the answer is part of the point. Wherever you are, in a city apartment where the sky is orange with light pollution, or in a quiet house where the actual stars are out, or somewhere in between, somewhere ordinary, somewhere that feels very far from the Coma Cluster and the Dragonfly telephoto array, and the underground liquid xenon of the LX Zeppelin detector. Wherever you are surrounded by the thing we have spent this night talking about. The dark matter is not somewhere else at a safe astronomical distance. It is here. It is the same halo that makes Vera Rubin's rotation curves flat. It is the same substance that walked through the bullet cluster collision while the gas got piled up behind. It is what DF2 is missing, and what that missing tells us must once have been there. If you have a comment to leave, and I hope you do, tell me where in the world you are listening from tonight and what time it is in your corner of the dark. Those 2 facts interest me more than almost anything else. And if this slow journey through the invisible architecture of the universe was something you found worth staying awake for, even a little, even at the edges of sleep where the words start to sound like water, a like, a subscribe, a small gesture toward this quiet channel. It means more than you might think. Small creators like me rely on your support to keep these nights going. Every one of those gestures is what makes the next script possible, the next late-night drift through some other corner of physics or history, or the strangeness of existing at all. The one-line version, if you want something to carry with you, a missing substance proves the substance exists because you cannot lose a law, but you can lose a thing. DF2 is the galaxy that lost its dark matter, and by losing it, showed us what dark matter is. Close the books, dim the lamp, class is over, sleepy scholar.